Hello, everyone. My name is Dr. Deepak Kumar. I have 15 years of experience of teaching chemistry. So today I'm going to make you understand by the topic called order of reaction and its determination by different methods. To move forward, we'll have to recall prerequisite knowledge points, which are reaction rates, rate equations, and factors affecting reaction rate. So, if I help you to recall all these knowledge points, so it goes like this, that reaction rate is defined as the change in concentration of the reactants or the products in the given time window. Rate equation gives the relation between the rate and the molar concentration terms of the reactant. Molar concentration term means here the molarity, that's unit is mole per liter, and then factor affecting reaction rates, which are as temperature, pressure, concentration, and catalyst. So let's move to our topic, today's topic. So before starting today's topic, I would just give you a question. If the concentration of a reactant doubles, how might the rate change? So, as I told you, the rate of reaction depends on the concentration. This is one of the factors. So, to discuss about this question, so you have to make pairs and then you have to share the ideas. Make pairs means you have to discuss this in pairs. Next to it, I cannot give you much time for this, so I'll just help you to understand how that concentration of reactant affects the rate of reaction. Yeah, rate of reaction is influenced by the concentration of reactants, but in different ways depending on the reaction order. And this is our topic for today, reaction order or order of reaction. It means we can tell the effect of concentration, or we can give the effect of concentration on rate of reaction once we know about the order of reaction. So what is this order of reaction? Let's move and let us understand. General rule for nth order of reaction that I'm going to help you here with an example. First, how important this order of reaction is. So we have the formula called x raised to the power n, that x here gives the concentration of the reactant and n is the order of reaction. So for example, if molar concentration triples and reaction is of second order, so the rate increases by 3 raised to the power 2, that is 9 times. So now I'm just asking you a question. If the molar concentration terms here doubles, then what would be the rate and by which factor that rate will increase? Take your time, take a pause in the video and just go for it and share. To understand the order of reaction and its determination, this is our today's task. Though I'll be spending very less time on this topic because the full topic will take much time. So let's move forward. Today's learning outcomes will be including to identify and define zero first second order reactions, use experimental data to determine the reaction order, interpret and construct rate, concentration, and concentration time graphs to identify reaction order, solve numerical problems involving the rate equations and rate constants. Let's move forward to the first step to identify the order of reaction and to know about the order of reaction. See, the order of reaction refers to the power to which concentration of reactants is raised in the rate equation, and that is also called rate law. It indicates how the rate of reaction depends on the concentration of reactant. So generally, the order of reaction that gives us the exact idea to which extent the rate of a reaction depends on the concentration of the reactants. The order may be zero, first, second, or fractional, depending on the reaction mechanism. So it means that the order of reaction is totally a experimental value. It can be determined by the experiments only by knowing the mechanism, reaction mechanism. And the overall order of reaction is the sum of the individual orders of all the reactants. How can we go about it? Just see the example. For this reaction, A plus B gives C. You can look at my cursor where it is moving. So rate can be written as K. R rate is equal to K, A raised to the power M, B raised to the power N. These are all molar concentration terms, means molarity of A and B. And here K is called as rate constant. For an example, here 2a plus b gives c, we can write the rate equation k is equal to a square b1. It means that reaction is second order with respect to a and first with respect to b. The overall order we can get it by adding the powers of all these molar concentration terms. 2 plus 1 is equal to 3. So by this, we can easily find the order of the reaction once we know the mechanism or once we know the rate equation or rate law. Next to this, the type of reaction orders, if I tell you, there are many types, but here we'll be dealing with zero, first, and second order of kinetics. So how zero order reaction? The rate is independent of the concentration of the reactant here, and how the expression or rate law is written for this is rate is equal to K. Here the molar concentration term of the reactant is not involved. You can see after integrating this equation, we got the expression here as integrated rate law. That molar concentration term of A is the remaining concentration, and molar concentration of A term naught is that is giving the initial concentration. K is the rate constant in the time taken for the reaction. T is the time taken. We plot two graphs here, A versus time, means concentration versus time, and rate versus concentration. So we get these graphs. In next slide, we'll be moving about it. And the unit of K is here, mole dm minus 3 and second minus 1, means mole per dm cube per second. Half-life for this is given. Half-life is equal to A naught by 2K. So here half-life of the zero order reaction is directly proportional to initial concentration of the reactant. Though in this class, we'll not be dealing with the half-life of the reaction. Examples for this is ammonia decomposition or enzyme catalyzed reactions. The graph, if you see the concentration versus time, it is a straight line, decreases with slope minus K, and the concentration decreases linearly over time here in this graph. Second graph, you can see rate versus concentration. So here rate is remaining constant with the change of the concentration, you can see, and we got the horizontal line here. So by using some data, experimental data given to us, we'll plot the graph accordingly. And if we get such graphs, then we can easily identify the order of reaction. Next is first order reaction. Here the rate is directly proportional to the concentration of the reactant, or the first power of the concentration terms of the reactant. For first order reaction kinetics, the rate expression can be given as rate law. Rate is equal to Ka molar concentration term. Then after integrating this equation, we get ln A is equal to ln A naught minus Kt. ln stands for standard log is equal to 2.303 log. We'll plot three graphs here, A versus time, ln A versus time, rate versus A. A is here, this under bracket, what is written here is molar concentration term, that is molarity of the reaction. The unit of K becomes here, means rate constant for first order reaction becomes second inverse. The half-life here by the formula itself, you can come to know that half-life of first order does not depend on the initial concentration of the reactant. Example, H2O2 decomposition means hydrogen peroxide and radioactive decay. One point to just recall here, if we just go through zero order kinetics, and if we see the half-life of zero order reaction, there a note was mentioned, and there the half-life of the reaction depends on the zero order reaction. Half-life of the zero order reaction depends on the initial concentration of the reactant, but for first order it is not. Next, if we see the graphs here, so concentration versus time, we get the graph and we get the exponential decay here, exponential decay. And in second, we get a straight line with slope minus k and the intercept ln a naught. This is called intercept. So this is ln a versus time. And third graph is rate versus concentration. So here you can see the linear line showing the directly proportional to the concentration. So from the graph itself, we'll decide or will determine the order of reaction. Next is the second order kinetics, and here second order kinetics indicates that rate depends on the square of the molar concentration term of the reactant, and the integrated rate law is given 1 by A by is equal to 1 by A naught plus KT. Three graphs again will be drawing. The unit of K becomes here dmq, mole inverse, second inverse, half-life. You can see here inversely proportional to the initial concentration. Examples, if you see, you can find NO2 dimerization and saponification of aster. There are many more other examples as well. Second order, if we see the graphs here, concentration versus time. So we get steep exponential decay here, and the concentration decreases faster than the first order reaction here. Second graph is, you can see 1 by A concentration versus time. So here we get the straight line with a slope of K, means positive slope, and with intercept is 1 by A naught. Third graph is again rate versus concentration of A. It gives a quadratic curve showing that rate increases proportionally to molar concentration in terms of reactant and its square. Next is determination of order of reaction. So here we have the methods of initial rate. So here we'll be having some data that concentration term of A, concentration term of B, and initial rates are given. How can we go about it? First, you can see, observe first and second experiments. The concentration of A becomes double here and B remaining same, but the initial rate is becoming 4 times. So for this, we'll write the rate law. You can see my cursor. The rate is equal to K A raised to the power M and B raised to the power N. Then what we'll do, we'll make the equations, rate equations, and we'll divide rate 2 by 1 and raised with the power M here. And by calculating it, we'll get the value of M is equal to 2. It means the rate of the reaction depends on the square of the molar concentration terms of reactant A. And the value of B means with respect to B reactant, how can we go about it? With the same rate, we'll be writing the expression, same kind of expression. And if you see equation here, what we have got from experiment number 2 and 3, the concentration of A remaining same and B is becoming double, and the initial rate is also getting double. So we just will put the values as we have put for the A reactant, and we'll get the value of N is equal to 1. So now we have got the value of MNN. So from here, we can easily get the expression, and by adding the powers of molar concentration in terms of the reactant, we'll get to know the order of reaction. So this data given here follows third order kinetics. Next is determination of the order of reaction by graphical method. That was initial rate method, now graphical method. So for graphical method, if we get a straight line by plotting a graph A versus time, ln A versus time, 1 by A versus time. So we'll be able to say that they belong to 0, first order, and second order respectively. Next is, suppose we have this data with us, and now if we plot a graph here, so we'll get the graph like this, and you can see here straight line. What we are getting for zero order reaction means A versus time. So it means the given data follows zero order reaction. For the same data, once we come to know that it follows zero order kinetics, we can calculate the value of rate constant as well. So how can we go about it? So we have the data, same data. Once we come to know the order of reaction, that was zero order. So now we'll put the zero order reaction or formula for that, that is integrated rate law formula. A dot indicates that concentration of A at zero time, and A concentration indicates that the concentration of A after 40 seconds. So just substituting these values here in the formula, and we'll get the value of K, rate constant here. The unit would be mole per liter second, or we can say mole liter inverse second inverse. So like this, we can calculate the rate constant once we come to know the order of reaction. And order of reaction will come to know by using a graphical method or initial rate method. Clear? Or I mean to say the mechanism of the reaction. So today in this session, we have learned how to determine order of reaction, how to calculate, then after rate constant for the given data. Now this is your time to do or to solve this problem. Take your time. I'll see you in the next class. Please see the recording. You will really find it useful. This is the question for your ease I've given on zero order kinetics only. So stay motivated. Thank you. Bye everyone.